Hello everyone, welcome to my audiobook. Today's lesson is from NCERT Chemistry, Part 1, Unit 4, Chemical Bonding and Molecular Structure. So let's start. Scientists are constantly discovering new compounds, orderly arranging the facts about them, trying to explain with the existing knowledge, organizing to modify the earlier views or evolve theories for explaining the newly observed facts. Matter is made up of one or different type of elements. Under normal conditions, no other element exists as an independent atom in nature except noble gases. However, a group of atoms is found to exist together as one species having characteristic properties. Such a group of atoms is called a molecule. Obviously, there must be some force which holds these constituent atoms together in the molecules. The attractive force which holds various constituents, that is atoms, ions, etc., together in different chemical species is called a chemical bond. Since the formation of chemical bond takes place as a result of combination of atoms of various elements in different ways, it raises many questions. Why do atoms combine? Why are only certain combinations possible? Why do some atoms combine while certain others do not? Why do molecules possess definite shapes? To answer such questions, different theories and concepts have been put forward from time to time. These are Cosell-Lewis approach, valency shell electron pair repulsion (VSEPR) theory, valency bond theory, and molecular orbital theory. The evolution of various theories of valency and the interpretation of the nature of chemical bonds have closely been related to the developments in the understanding of the structure of atom, the electronic configuration of elements, and the periodic table. Every system tends to be more stable, and bonding is nature's way of lowering the energy of the system to attain stability. Next, Cosell-Lewis approach to chemical bonding. In order to explain the formation of chemical bond in terms of electrons, a number of attempts were made, but it was only in 1916 when Cosell and Lewis succeeded independently in giving a satisfactory explanation. They were the first to provide some logical explanations of valency, which was based on the inertness of noble gases. Lewis pictured the atom in terms of a positively charged kernel, the nucleus plus the inner electrons, and the outer shell that could accommodate a maximum of 8 electrons. He further assumed that these 8 electrons occupy the corners of a cube which surround the kernel. Thus, the single outer shell electron of sodium would occupy one corner of the cube, while in the case of a noble gas, all the 8 corners would be occupied. This octet of electrons represents a particularly stable electronic arrangement. Lewis postulated that atoms achieve the stable octet when they are linked by chemical bonds. In the case of sodium and chlorine, this can happen by the transfer of an electron from sodium to chlorine, thereby giving the Na plus and Cl minus ions. In the case of other molecules like Cl2, hydrogen, F2, etc., the bond is formed by the sharing of a pair of electrons between the atoms. In the process, each atom attains a stable outer octet of electrons. Lewis symbols. In the formation of a molecule, only the outer shell electrons takes part in chemical combination, and they are known as valency electrons. The inner shell electrons are well protected and are generally not involved in the combination process. G.N. Lewis, an American chemist, introduced simple notations to represent valency electrons in an atom. These notations are called Lewis symbols. For example, the Lewis symbols for the elements of second period are as under. You can check it out here. Significance of Lewis symbols. The number of dots around the symbol represents the number of valency electrons. This number of valency electrons help to calculate the common or group valency of the element. The group valency of the elements is generally either equal to the number of dots in Lewis symbols or 8 minus the number of dots or valency electrons. Cosell, in relation to chemical bonding, drew attention to the following facts. First one, in the periodic table, the highly electronegative halogens and the highly electropositive alkali metals are separated by the noble gases. The formation of a negative ion from a halogen atom and a positive ion from an alkali metal atom is associated with a gain and loss of an electron by the respective atoms. The negative and positive ions thus formed attain stable noble gas electronic configurations. The noble gases, with the exception of helium, which has a duplet of electrons, have a particularly stable outer shell configuration of 8 octet electrons, Ns2, Np6. The negative and positive ions are stabilized by electrostatic attraction. For example, the formation of NaCl from sodium and chlorine according to the above scheme can be explained as sodium gives rise to Na++ electron, neon 3s1, chlorine plus electron gives Cl minus, sodium plus Na plus Cl minus gives NaCl or Na plus Cl minus. Similarly, the formation of CaF2 may be shown as Ca gives rise to Ca plus 2 electrons. F plus 1 electron gives rise to F minus. Ca plus 2 F minus gives CaF2 or Ca plus 2 F minus 2. The bond formed as a result of the electrostatic attraction between the positive and negative ions was termed as the electrovalent bond. The electrovalency is thus equal to the number of unit charge or charges on the ion. Thus, calcium is assigned a positive electrovalency of 2 while chlorine a negative electrovalency of 1. Cosell's postulations provide the basis for the modern concepts regarding ionic formation by electron transfer and the formation of ionic crystalline compounds. His views have proved to be a great value in understanding and systemization of the ionic compounds. At the same time, he did recognize the fact that a large number of compounds did not fit into these concepts. Next, octet rule. Cosell and Lewis in 1916 developed an important theory of chemical combination between atoms known as electronic theory of chemical bonding. According to this, atoms can combine either by transfer of valency electrons from one atom to another, gaining or losing, or by sharing of valency electrons in order to have an octet in their valency shells. This is known as octet rule. Next is covalent bond. Langmuir 1919 refined the Lewis postulations by abandoning the idea of the stationary cubical arrangement of the octet and by introducing the term covalent bond. The Lewis-Langmuir theory can be understood by considering the formation of the chlorine molecule Cl2. The Cl atom with electronic configuration 3s2 3p5 is 1 electron short of the argon configuration. The formation of the Cl2 molecule can be understood in terms of the sharing of a pair of electrons between the two chlorine atoms, each chlorine atom contributing 1 electron to the shared pair. In the process, both chlorine atoms attain the outer shell octet of the nearest noble gas, that is argon. The dots represent electrons. Such structures are referred to as Lewis dot structures. The Lewis dot structures can be written for other molecules also, in which the combining atoms may be identical or different. The important conditions being that, first one, each bond is formed as a result of sharing of an electron pair between the atoms. Second point, each combining atom contributes at least 1 electron to the shared pair. Next point, the combining atoms attain the outer shell noble gas configurations as a result of the sharing of electrons. Fourth point, thus in water and carbon tetrachloride molecules, formation of covalent bonds can be represented as so here H atoms attain a duplet of electrons and O, the octet. Okay, these figures I will provide you. You can check it out. Thus, when two atoms share one electron pair, they are said to be joined by a single covalent bond. In many compounds, we have multiple bonds between atoms. The formation of multiple bonds envisages sharing of more than one electron pair between two atoms. If two atoms share two pairs of electrons, the covalent bond between them is called a double bond. For example, in the carbon dioxide molecule, we have two double bonds between the carbon and oxygen atoms. Similarly, in ethane molecule, the two carbon atoms are joined by a double bond. Okay, you can check the figures over here. Next, when combining atoms share three electron pairs, as in the case of two nitrogen atoms in the N2 molecule and the two carbon atoms in the ethane molecule, a triple bond is formed. Next, Lewis representation of simple molecules, the Lewis structures. The Lewis dot structures provide a picture of bonding in molecules and ions in terms of the shared pairs of electrons and the octet rule. While such a picture may not explain the bonding and behavior of a molecule completely, it does help in understanding the formation and properties of a molecule to a large extent. Writing of Lewis dot structures of molecules is therefore very useful. The Lewis dot structures can be written by adopting the following steps. First one, the total number of electrons required for writing the structures are obtained by adding the valency electrons of the combining atoms. For example, in the CH4 molecule, there are 8 valency electrons available for bonding, 4 from carbon and 4 from the 4 hydrogen atoms. Second point, for anions, each negative charge would mean addition of 1 electron. For cations, each positive charge would result in a subtraction of 1 electron from the total number of valency electrons. For example, for the CO3 minus 2 ion, the two negative charges indicate that there are 2 additional electrons than those provided by the neutral atoms. For NH4 plus ion, one positive charge indicates the loss of 1 electron from the group of neutral atoms. Next point, knowing the chemical symbols of the combining atoms and having knowledge of the skeletal structures of the compound, known or guessed intelligently, it is easy to distribute the total number of electrons as bonding shared pairs between the atoms in proportion to the total bonds. In general, the least electronegative atom occupies a central position in the molecule or ion. For example, in the NF3 and CO3 minus 2, nitrogen and carbon are the central atoms, whereas fluorine and oxygen occupy the terminal positions. Next point, after counting for the shared pairs of electrons for single bonds, the remaining electron pairs are either utilized for multiple bonding or remain as the lone pairs. The basic requirement being that each bonded atom gets an octet of electrons. Lewis representations of a few molecules or ions are given in table 4.1. So this table I will be providing you at the end of this audiobook. Okay, as well as they have given the problems also. These also I will provide. Next, formal charge. Lewis dot structures in general do not represent the actual shapes of the molecules. In case of polyatomic ions, the net charge is possessed by the ion as a whole and not by a particular atom. It is, however, feasible to assign a formal charge on each atom. The formal charge of an atom in a polyatomic molecule or ion may be defined as a difference between the number of valency electrons of that atom in an isolated or free state and the number of electrons assigned to that atom in the Lewis structure. Next, the counting is based on the assumption that the atom in the molecule owns 1 electron of each shared pair and both the electrons of a lone pair. Let us consider the ozone molecule O3. The Lewis structure of O3 may be drawn as, so this is structure. The atoms have been numbered as 1, 2 and 3. The formal charge on the central O atom marked 1 equals to 6 minus 2 minus 1 by 2 into 6 equals to plus 1. The end 0 atom marked 2, that is the end O atom marked 2, which gives rise to 0, the formal charge is 0. The end O atom marked 3 gives minus 1. Hence we represent O3 along with the formal charges as follows. We must understand that formal charges do not indicate real charge separation within the molecule. Indicating the charges on the atoms in the Lewis structure only helps in keeping track of the valency electrons in the molecule. Formal charges help in the selection of the lowest energy structure from a number of possible Lewis structures for a given species. Generally, the lowest energy structure is the one with the smallest formal charges on the atoms. The formal charge is a factor based on a pure covalent view of bonding in which electron pairs are shared equally by neighboring atoms. Next, limitations of the octet rule. The octet rule, though useful, is not universal. It is quite useful for understanding the structures of most of the organic compounds, and it applies mainly to the second period element of the periodic table. There are 3 types of exemptions to the octet rule. The incomplete octet of the central atom. In some compounds, the number of electrons surrounding the central atom is less than 8. This is especially the case with elements having less than 4 valency electrons. Examples are lithium chloride, beryllium BeH2 and BCl3. Li, Be and B have 1, 2 and 3 valency electrons only. Some other such compounds are AlCl3 and BF3. Next, odd electron molecules. In molecules with an odd number of electrons like nitric oxide, NO and nitrogen dioxide, NO2, the octet rule is not satisfied for all the atoms. Next, the expanded octet. Elements in and beyond the third period of the periodic table have, apart from 3s and 3p orbitals, 3d orbitals also available for bonding. In a number of compounds of these elements, there are more than 8 valency electrons around the central atom. This is termed as the expanded octet. Obviously, the octet rule does not apply in such cases. Some of the examples of such compounds are PF5, SF6, H2SO4 and a number of coordination compounds. Interestingly, sulfur also forms many compounds in which the octet rule is obeyed. In sulfur dichloride, the S atom has an octet of electrons around it. Other drawbacks of the octet theory. First one. It is clear that octet rule is based upon the chemical inertness of the noble gases. However, some noble gases, for example xenon and krypton, also combine with oxygen and fluorine to form a number of compounds like XeF2, KrF2, XeOF2, etc. Second point, this theory does not account for the shape of molecules. Next point, it does not explain the relative stability of the molecules, being totally silent about the energy of the molecule. Next, ionic or electrovalent bond. From the Cosell and Lewis treatment of the formation of an ionic bond, it follows that the formation of ionic compounds would primarily depend upon, first point, the ease of formation of the positive and negative ions from the respective neutral atoms. Second point, the arrangement of the positive and the negative ions in the solid, that is, the lattice of the crystalline compound. The formation of the positive ion involves ionization, that is, removal of electrons from the neutral atom, and that of the negative ion involves the addition of electron to the neutral atom. The electron gain enthalpy is the enthalpy change when a gas phase atom in its ground state gains an electron. The electron gain process may be exothermic or endothermic. The ionization, on the other hand, is always endothermic. Electron affinity is the negative of the energy change accompanying electron gain. Obviously, ionic bonds will be formed more easily between elements with comparatively low ionization enthalpies and elements with comparatively high negative value of electron gain enthalpy. Most ionic compounds have cations derived from metallic elements and anions from non-metallic elements. The ammonium ion NH4 plus made up of two non-metallic elements is an exception. It forms the cation of a number of ionic compounds. Ionic compounds in the crystalline state consist of orderly three-dimensional arrangements of cations and anions held together by Coulombic interaction energies. These compounds crystallize in different crystal structures determined by the size of the ions, their packing arrangements and other factors. The crystal structure of sodium chloride, NaCl, rock salt for example is shown below. Okay, I'll give you the picture. In ionic solids, the sum of the electron gain enthalpy and the ionization enthalpy may be positive, but still the crystal structure gets stabilized due to the energy released in the formation of the crystal lattice. For example, the ionization enthalpy for Na plus formation from Na is 495.8 kilojoules per mole, while the electron gain enthalpy for the change Cl plus 1 electron gives Cl minus is minus 348.7 kilojoules per mole only. The sum of the two, 147.1 kilojoules per mole, is more than compensated for by the enthalpy of lattice formation of NaCl, minus 788 kilojoules per mole. Therefore, the energy released in the process is more than the energy absorbed. Thus, a qualitative measure of the stability of an ionic compound is provided by its enthalpy of lattice formation and not simply by achieving octet of electrons around the ionic species in gaseous state. Since lattice enthalpy plays a key role in the formation of ionic compounds, it is important that we learn more about it. Next is lattice enthalpy. The lattice enthalpy of an ionic solid is defined as the energy required to completely separate 1 mole of a solid ionic compound into gaseous constituent ions. For example, the lattice enthalpy of NaCl is 788 kilojoules per mole. This means that 788 kilojoules of energy is required to separate 1 mole of solid NaCl into 1 mole of Na plus and 1 mole of Cl minus to an infinite distance. This process involves both the attractive forces between ions of opposite charges and the repulsive forces between ions of like charge. The solid crystal being three-dimensional, it is not possible to calculate lattice enthalpy directly from the interaction of forces of attraction and repulsion only. Factors associated with the crystal geometry have to be included. Next, bond parameters. In that first one, bond length. Bond length is defined as the equilibrium distance between the nuclei of two bonded atoms in a molecule. Bond lengths are measured by spectroscopic, X-ray diffraction and electron diffraction techniques about which you will learn in higher classes. Each atom of the bonded pair contributes to the bond length. In the case of a covalent bond, the contribution from each atom is called the covalent radius of that atom. The covalent radius is measured approximately as the radius of an atom's core which is in contact with the core of an adjacent atom in a bonded situation. The covalent radius is half of the distance between two similar atoms joined by a covalent bond to the same molecule in the same molecule. The van der Waals radius represents the overall size of the atom which includes its valency shell in a non-bonded situation. Further, the van der Waals radius is half of the distance between two similar atoms in separate molecules in a solid. Covalent and van der Waals radii of chlorine are depicted in figure 4.2. You can check it out. I will provide you this figure also. Some typical average bond lengths for single, double and triple bonds are shown in table 4.2. Bond lengths for some common molecules are given in table 4.3. The covalent radii of some common elements are listed in table 4.4. All these tables I will provide you. Next is bond angle. It is defined as the angle between the orbitals containing bonding electron pairs around the central atom in a molecule or complex ion. Bond angle is expressed in degree, which can be experimentally determined by spectroscopic methods. It gives some idea regarding the distribution of orbitals around the central atom in a molecule or complex ion, and hence it helps us in determining its shape. For example, HOH bond angle in water can be represented as under. The angle is 104.5 degrees. Next is bond enthalpy. It is defined as the amount of energy required to break 1 mole of bonds of a particular type between two atoms in a gaseous state. The unit of bond enthalpy is kilojoules per mole. For example, the HH bond enthalpy in hydrogen molecule is 435.8 kilojoules per mole. Similarly, the bond enthalpy for the molecules containing multiple bonds, for example, O2 and N2 will be for O2 it is 498 kilojoules per mole, and for N2 it is 946 kilojoules per mole. It is important that larger the bond dissociation enthalpy, stronger will be the bond in the molecule. For a heteronuclear diatomic molecules like HCl, we have HCl gives rise to H plus Cl. The enthalpy is 431 kilojoules per mole. In case of polyatomic molecules, the measurement of bond strength is more complicated. For example, in case of H2O molecule, the enthalpy needed to break the two OH bonds is not the same. The difference in the delta H values shows that the second OH bond undergoes some change because of changed chemical environment. This is the reason for some difference in energy of the same OH bond in different molecules like C2H5OH, ethanol and water. Therefore, the polyatomic molecules and term mean or average bond enthalpy is used. It is obtained by dividing total bond dissociation enthalpy by the number of bonds broken as explained below in the case of water molecule. So average bond enthalpy equals to 502 plus 427 divided by 2 equals to 464.5 kilojoules per mole. Next is bond order. In the Lewis description of covalent bond, the bond order is given by the number of bonds between the two atoms in a molecule. The bond order, for example, in H2 with a single shared electron pair, in O2 with two shared electron pairs, and in N2 with three shared electron pairs is 1, 2, 3 respectively. Similarly, in CO, three shared electron pairs between C and O, the bond order is 3. For N2, bond order is 3 and its enthalpy is 946 kilojoules per mole, being one of the highest for a diatomic molecule. Isoelectronic molecules and ions have identical bond orders. For example, F2 and O2-2 have bond order 1. N2, CO and NO plus have bond order 3. The general correlation useful for understanding the stabilities of molecules is that with increase in bond order, bond enthalpy increases and bond length decreases. Next one. Resonance structures. It is often observed that a single Lewis structure is inadequate for the representation of a molecule in conformity with the experimentally determined parameters. For example, the ozone O3 molecule can be equally represented by the structures 1 and 2 shown below. So what are the structures? Let us see. Okay, these are the structures. Resonance in the O3 molecules. The pictures I will provide you. You can check it out. In both structures, we have a O single bond O and a O double bond O. O double bond O. The normal O single bond O and O double bond O bond lengths are 148 pm and 121 pm respectively. Experimentally determined oxygen to oxygen bond lengths in the O3 molecule are same, 128 pm. Thus, the oxygen to oxygen bonds in the O3 molecules are intermediate between a double and a single bond. Obviously, this cannot be represented by either of the two Lewis structures shown above. The concept of resonance was introduced to deal with the type of difficulty experienced in the depiction of accurate structures of molecules like O3. According to the concept of resonance, whenever a single Lewis structure cannot describe a molecule accurately, a number of structures with similar energy, positions of nuclei, bonding and non-bonding pairs of electrons are taken as the canonical structures of a hybrid which describes the molecule accurately. Thus, for O3, the two structures shown above constitute the canonical structures or resonance structures, and their hybrid, that is, the 3 structure represents the structure of O3 more accurately. This is also called resonance hybrid. Resonance is represented by a double-headed arrow. Some of the other examples of the resonance structures are provided by the carbonate ion and the carbon dioxide molecule. Next, in general, it may be stated that, first point, resonance stabilizes the molecule as the energy of the resonance hybrid is less than the energy of any single canonical structure. And second point, resonance averages the bond characteristics as a whole. Thus, the energy of the O3 resonance hybrid is lower than either of the two canonical forms 1 and 2. There is a green box here, let us see. Many misconceptions are associated with resonance and the same need to be dispelled. You should remember that. First point, the canonical forms have no real existence. Second point, the molecule does not exist for a certain fraction of time in one canonical form and for other fractions of time in other canonical forms. Third point, there is no such equilibrium between the canonical forms as we have between tautomeric forms, keto and enol in tautomerism. Next, fourth point, the molecule as such has a single structure which is a resonance hybrid of the canonical forms and which cannot as such be depicted by a single Lewis structure. Next, polarity of bonds. The existence of a 100% ionic or covalent bond represents an ideal situation. In reality, no bond or a compound is either completely covalent or ionic. Even in case of covalent bond between two hydrogen atoms, there is some ionic character. When covalent bond is formed between two similar atoms, for example in H2, O2, Cl2, N2 and F2, the shared pair of electrons is equally attracted by the two atoms. As a result, electron pair is situated exactly between the two identical nuclei. The bond so formed is called non-polar covalent bond. Contrary to this, in case of a heteronuclear molecule like HF, the shared electron pair between the two atoms gets displaced more towards fluorine since the electronegativity of fluorine is far greater than that of hydrogen. The resultant covalent bond is a polar covalent bond. As a result of polarization, the molecule possesses the dipole moment, which can be defined as a product of the magnitude of the charge and the distance between the centers of positive and negative charge. It is usually designated by a Greek letter mu. Mathematically, it is expressed as follows. Dipole moment equals to charge into distance of separation. Dipole moment is usually expressed in dBA units. The conversion factor is 1D equals to 3.33564 into 10 to the power of minus 30 cm, where C is coulomb and m is meter. Further, dipole moment is a vector quantity and by convention it is depicted by a small arrow with tail on the negative center and head pointing towards the positive center. But in chemistry, presence of dipole moment is represented by the crossed arrow put on Lewis structure of a molecule. The cross is on positive end and arrow head is on negative end. For example, the dipole moment of HF may be represented as like this. This arrow symbolizes the direction of the shift of electron density in the molecule. Note that the direction of crossed arrow is opposite to the conventional direction of dipole moment. They have given about Peter Debye. The Dutch chemist received Nobel Prize in 1936 for his work on X-ray diffraction and dipole moments. The magnitude of the dipole moment is given in Debye units in order to honor him. In case of polyatomic molecules, the dipole moment not only depend upon the individual dipole moments of bonds known as bond dipoles, but also on the spatial arrangement of various bonds in the molecule. In such case, the dipole moment of a molecule is a vector sum of the dipole moments of various bonds. For example, in H2O molecule, which has a bent structure, the two OH bonds are oriented at an angle of 104.5 degrees. Net dipole moment of 6.17 into 10 to the power of minus 30 coulomb meter is the resultant of the dipole moments of two OH bonds. Net dipole moment mu equal to 1.85 D equals to 6.17 into 10 to the power of minus 30 cm. The dipole moment in case of BeF2 is 0. This is because the two equal bond dipoles point in opposite directions and cancel the effect of each other. In tetraatomic molecule, for example, in BF3, the dipole moment is 0, although the BF bonds are oriented at an angle of 120 degrees to one another. The three bond moments give a net sum of 0 as the resultant of any two is equal and opposite to the third. Let us study an interesting case of NH3 and NF3 molecule. Both the molecules have pyramidal shape with a lone pair of electrons on nitrogen atom. Although fluorine is more electronegative than nitrogen, the resultant dipole moment of NH3 is greater than that of NF3. This is because in case of NH3, the orbital dipole due to lone pair is in the same direction as the resultant dipole moment of NH bonds, whereas in NF3, the orbital dipole is in the direction opposite to the resultant dipole moment of the 3NF bonds. The orbital dipole, because of lone pair, decreases the effect of the resultant NF bond moments, which results in the low dipole moment of NF3 as represented below. You can check the figures here. Dipole moments of some molecules are shown in table 4.5. This is 4.5. This table I will provide you. Just as all the covalent bonds have some partial ionic character, the ionic bonds also have partial covalent character. The partial covalent character of ionic bonds was discussed by Fazens in terms of the following rules. First one. The smaller the size of the cation and larger the size of anion, the greater the covalent character of an ionic bond. Second point, the greater the charge on the cation, the greater the covalent character of the ionic bond. Next point, for cations of the same size and charge, the one with electronic configuration DNNS0 typical of transition metals is more polarizing than the one with a noble gas configuration NS2NP6 typical of alkali and alkaline earth metal cations. The cation polarizes the anion, pulling the electronic charge toward itself and thereby increasing the electronic charge between the two. This is precisely what happens in a covalent bond, that is, buildup of electron charge density between the nuclei. The polarizing power of the cation, the polarizability of an anion, and the extent of distortion, polarization of anion, and the factors which determine the percent covalent character of the ionic bond. Next is the valency shell electron pair repulsion, VSEPR theory. As already explained, Lewis' concept is unable to explain the shapes of molecules. This theory provides a simple procedure to predict the shapes of covalent bonds. Sedgwick and Powell in 1940 proposed a simple theory based on the repulsive interactions of the electron pairs in the valency shell of the atoms. It was further developed and redefined by Nielom and Gillespie, 1957. The main postulates of VSEPR theory are as follows. First one, the shape of a molecule depends upon the number of valency shell electron pairs, bonded or non-bonded, around the central atom. Next point, pairs of electrons in the valency shell repel one another since their electron clouds are negatively charged. Next one, these pairs of electrons tend to occupy such positions in space that minimize repulsion and thus maximize distance between them. Next point, the valency shell is taken as a sphere with the electron pairs localizing on the spherical surface at maximum distance from one another. Next point, a multiple bond is treated as if it is single electron pair and the 2 or 3 electron pairs of the multiple bond are treated as a single super pair. Next point, where 2 or more resonance structures can represent a molecule, the VSEPR model is applicable to any such structure. The repulsive interaction of electron pairs decrease in the order lone pair greater than lone pair, bond pair greater than bond pair, bond pair. Okay, I'll give you this, you can check it out. Nielom and Gillespie 1957 refined the VSEPR model by explaining the important difference between the lone pairs and bonding pairs of electrons. While the lone pairs are localized on the central atom, each bonded pair is shared between two atoms. As a result, the lone pair electrons in a molecule occupy more space as compared to the bonding pairs of electrons. This results in greater repulsion between lone pairs of electrons as compared to the lone pair, bond pair and bond pair repulsions. These repulsion effects results in deviations from idealized shapes and alterations in both angles in molecule. For the production of geometrical shapes of the molecules with the help of VSEPR theory, it is convenient to divide molecules into two categories as first one, molecules in which the central atom has no lone pair, and the second one, molecules in which the central atom has one or more lone pairs. Table 4.6 shows the arrangement of electron pair about the central atom A without any lone pairs and geometries of some molecules or ions of the type AB. Table 4.7 shows shapes of some of simple molecules and ions in which the central atom has one or more lone pairs. Table 4.8 explains the reasons for the distortions in the geometry of the molecule. As depicted in Table 4.6, in the compounds of AB2, AB3, AB4, AB5 and AB6, the arrangement of electron pairs and the B atoms around the central atom A are linear, trigonal, planar, tetrahedral, trigonal, bipyramidal and octahedral respectively. Such arrangement can be seen in the molecules like BF3, that is AB3, CH4, that is AB4 and PCl5, that is AB5, as depicted below by their ball and stick models. This figure you can see. The VSEPR theory is able to predict geometry of a large number of molecules, especially the compounds of P block elements, accurately. It is also quite successful in determining the geometry quite accurately even when the energy difference between possible structures is very small. The theoretical basis of the VSEPR theory regarding the effects of electron pair repulsions on molecular shapes is not clear and continues to be a subject of doubt and discussion. So here is a table shows geometry of molecules in which the central atom has no lone pair of electrons. This table I will provide you, you can check it out. Okay, two tables were given. Okay, 3 pages and okay, next, valency bond theory. As we know that Lewis' approach helps in writing the structure of molecules, but it fails to explain the formation of chemical bond. It also does not give any reason for the difference in bond dissociation enthalpies and bond lengths in molecules like H2. and F2. Although in both the cases a single covalent bond is formed by the sharing of an electron pair between the respective atoms. It also gives no idea about the shapes of polyatomic molecules. Similarly, the VSEPR theory gives a geometry of simple molecules, but theoretically it does not explain them, and also it has limited applications. To overcome these limitations, the two important theories based on quantum mechanical principles are introduced. These are valency bond theory and molecular orbital theory. Valency bond theory was introduced by Heitler and London 1927 and developed further by Pauling and others. A discussion of the valency bond theory is based on the knowledge of atomic orbitals, electronic configuration of elements, the overlap criteria of atomic orbitals, the hybridization of atomic orbitals, and the principles of variation and superposition. A rigorous treatment of the VB theory in terms of these aspects is beyond the scope of this book. Therefore, for the sake of convenience, valency bond theory has been discussed in terms of qualitative and non-mathematical treatment only. To start with, let us consider the formation of hydrogen molecule, which is the simplest of all molecules. Consider two hydrogen atoms A and B approaching each other having nuclei Na and Nb, and electrons present in them are represented by Ea and Eb. When the two atoms are at large distance from each other, there is no interaction between them. As these two atoms approach each other, new attractive and repulsive forces begin to operate. Attractive forces arise between, first point, nucleus of one atom and its own electron, that is Na minus Ea, and sorry, not minus, it is bond, and Nb Eb. Next, second point, nucleus of one atom and electron of other atom, Na Eb Nb Ea. Similarly, repulsive forces arise between, first one, electrons of two atoms like Ea Eb, next, nuclei of two atoms Na Nb. Attractive forces tend to bring the two atoms close to each other, whereas repulsive forces tend to push them apart. Experimentally, it has been found that the magnitude of new attractive force is more than the new repulsive forces. As a result, two atoms approach each other and potential energy decreases. Ultimately, a stage is reached where the net force of attraction balances the force of repulsion and system acquires minimum energy. At this stage, two hydrogen atoms are said to be bonded together to form a stable molecule having the bond length of 74 pm. Since the energy gets released when the bond is formed between the two hydrogen atoms, the hydrogen molecule is more stable than that of isolated hydrogen atoms. The energy so released is called as bond enthalpy, which is corresponding to minimum in the curve depicted in figure 4.8. Conversely, 435.8 kilojoules of energy is required to dissociate 1 mole of H2 molecule. Next is orbital overlap concept. In the formation of hydrogen molecule, there is a minimum energy state when two hydrogen atoms are so near that their atomic orbitals undergo partial interpenetration. This partial merging of atomic orbitals is called overlapping of atomic orbitals, which results in the pairing of electrons. The extent of overlap decides the strength of a covalent bond. In general, greater the overlap, the stronger is a bond formed between two atoms. Therefore, according to orbital overlap concept, the formation of a covalent bond between two atoms results by pairing of electrons present in the valency shell having opposite spins. Next is directional properties of bonds. As we have already seen, the covalent bond is formed by overlapping of atomic orbitals. The molecule of hydrogen is formed due to the overlap of 1s orbitals of two H atoms. In case of polyatomic molecules like CH4, NH3 and H2O, the geometry of the molecules is also important in addition to the bond formation. For example, why is it so that CH4 molecule has tetrahedral shape and HCH bond angles are 109.5 degrees? Why is the shape of NH3 molecule pyramidal? The valency bond theory explains the shape, the formation, and directional properties of bonds in polyatomic molecules like CH4, NH3, and H2O, etc., in terms of overlap and hybridization of atomic orbitals. Next, overlapping of atomic orbitals. When orbitals of two atoms come close to form bond, their overlap may be positive, negative, or zero depending upon the sign, phase, and direction of orientation of amplitude of orbital wave function in space, figure 4.9. Positive and negative sign on boundary surface diagrams in the figure 4.9 show the sign of orbital wave function are not related to charge. Orbitals forming bond should have same sign and orientation in space. This is called positive overlap. Various overlaps of S and P orbitals are depicted in figure 4.9. So this is figure 4.9. Okay, you can check it out. Just I will give you some pause here, you can check. Okay, the criterion of overlap as the main factor for the formation of covalent bonds applies uniformly to the homonuclear, heteronuclear diatomic molecules and polyatomic molecules. We know that the shapes of CH4, NH3 and H2O molecules are tetrahedral, pyramidal and bent respectively. It would be therefore interesting to use VB theory to find out if these geometrical shapes can be explained in terms of the orbital overlaps. Let us first consider the CH4 methane molecule. The electronic configuration of the carbon in its ground state is 2s2 2p2, which is in the excited state becomes 2s1 2p x1 2p y1 2p z1. The energy required for this excitation is compensated by the release of energy due to overlap between the orbitals of carbon and the hydrogen. The four atomic orbitals of carbon, each with an unpaired electron, can overlap with the 1s orbitals of the four hydrogen atoms which are also singly occupied. This will result in the formation of four CH bonds. It will, however, be observed that while the three p orbitals of the carbon are at 90 degrees to one another, the HCH angle for these will be 90 degrees. That is, three CH bonds will be oriented at 90 degrees to one another. The 2s orbital of carbon and the 1s orbital of H and spherically symmetrical and they can overlap in any direction. Therefore, the direction of the fourth CH bond cannot be ascertained. This description does not fit in with the tetrahedral HCH angles of 109.5 degrees. Clearly, it follows that simple atomic orbital overlap does not account for the directional characteristics of bonds in CH4. Using similar procedure and arguments, it can be seen that in the case of NH3 and H2O molecules, the HNH and HOH angles should be 90 degrees. This is in disagreement with the actual bond angles of 107 degrees and 104.5 degrees in the NH3 and H2O molecules respectively. Next, types of overlapping and nature of covalent bonds. The covalent bond may be classified into two types depending upon the types of overlapping. First one, sigma bond. Second one, pi bond. Sigma bond. This type of covalent bond is formed by the end-to-end head-on overlap of bonding orbitals along the internuclear axis. This is called as head-on overlap or axial overlap. This can be formed by any one of the following types of combinations of atomic molecules. SS overlapping. In this case, there is overlap of two half-filled s orbitals along the internuclear axis as shown below. Next, sp overlapping. This type of overlap occurs between half-filled s orbitals of one atom and half-filled p orbitals of another atom. Next is pp overlapping. This type of overlap takes place between half-filled p orbitals of the two approaching atoms. Next is pi bond. In the formation of pi bond, the atomic orbitals overlap in such a way that their axes remain parallel to each other and perpendicular to the internuclear axis. The orbitals formed due to sidewise overlapping consist of two saucer-type charged clouds above and below the plane of the participating atoms. Next is strength of sigma and pi bonds. Basically, the strength of the bond depends upon the extent of overlapping. In case of sigma bond, the overlapping of orbital takes place to a larger extent. Hence, it is stronger as compared to the pi bond where the extent of overlapping occurs to a smaller extent. Further, it is important to note that in the formation of multiple bonds between two atoms of the molecule, pi bond is formed in addition to the sigma bond. Next is hybridization. In order to explain the characteristic geometrical shapes of polyatomic molecules like CH4, NH3 and H2O, etc., Pauling introduced the concept of hybridization. According to him, the atomic orbitals combine to form new set of equivalent orbitals known as hybrid orbitals. Unlike pure orbitals, the hybrid orbitals are used in bond formation. The phenomenon is known as hybridization, which can be defined as a process of intermixing of the orbitals of slightly different energies so as to redistribute their energies, resulting in the formation of new set of orbitals of equivalent energies and shape. For example, when 1 2s and 3 2p orbitals of carbon hybridize, there is a formation of 4 new sp3 hybrid orbitals. Next, salient features of hybridization. The main features of hybridization are as under. First point, the number of hybrid orbitals is equal to the number of atomic orbitals that get hybridized. Second point, the hybridized orbitals are always equivalent in energy and shape. Third point, the hybrid orbitals are more effective in forming stable bonds than the pure atomic orbitals. Fourth point, these hybrid orbitals are directed in space in some preferred directions to have minimum repulsion between electron pairs and thus a stable arrangement. Therefore, the type of hybridization indicates the geometry of the molecules. Next is important conditions for hybridization. First point, the orbitals present in the valency shell of the atom are hybridized. Second point, the orbitals undergoing hybridization should have almost equal energy. Next, third point, promotion of electrons is not essential condition prior to hybridization. Fourth point, it is not necessary that only half-filled orbitals participate in hybridization. In some cases, even filled orbitals of valency shell take part in hybridization. Next, types of hybridization. There are various types of hybridization involving s, p and d orbitals. The different types of hybridization are as under. First one, sp hybridization. This type of hybridization involves the mixing of one s and one p orbital, resulting in the formation of two equivalent sp hybrid orbitals. The suitable orbitals for sp hybridization are s and pz if the hybrid orbitals are to lie along the z-axis. Each sp hybrid orbitals has 50% s character and 50% p character. Such a molecule in which the central atom is sp hybridized and linked directly to two other central atoms possess linear geometry. This type of hybridization is also known as diagonal hybridization. The two sp hybrids point in the opposite direction along the z-axis with projecting positive lobes and very small negative lobes, which provides more effective overlapping, resulting in the formation of stronger bonds. Example of molecule having sp hybridization: BeCl2, beryllium chloride. The ground state electronic configuration of Be is 1s2 2s2. In the excited state, one of the 2s electrons is promoted to vacant 2p orbital to account for its bivalency. One 2s and one 2p orbital gets hybridized to form two sp hybridized orbitals. These two sp hybrid orbitals are oriented in opposite direction, forming an angle of 180 degrees. Each of the sp hybridized orbital overlaps with 2p orbital of chlorine axially and form two BeCl sigma bonds. This is shown in figure 4.10. This is the figure Just you can have a look at it. Next is sp2 hybridization. In this hybridization, there is involvement of 1s and 2 p orbitals in order to form 3 equivalent sp2 hybridized orbitals. For example, in BCl3 molecule, the ground state electronic configuration of central boron atom is 1s2, 2s2, 2p1. In the excited state, one of the 2s electrons is promoted to vacant 2p orbital. As a result, boron has 3 unpaired electrons. These 3 orbitals, 1 2s and 2 2p, hybridize to form 3 sp2 hybrid orbitals. The 3 hybrid orbitals so formed are oriented in a trigonal planar arrangement and overlap with 2p orbitals of chlorine to form 3 BCl bonds. Therefore, in BCl3, the geometry is trigonal planar with Cl-BCl bond angle of 120 degrees. You can see the figure over here. Okay, right. Next, sp3 hybridization. This type of hybridization can be explained by taking the example of CH4 molecule, in which there is mixing of 1 s orbital and 3 p orbitals of the valency shell to form 4 sp3 hybrid orbitals of equivalent energies and shape. There is 25% s character and 75% p character in each sp3 hybrid orbital. The 4 sp3 hybrid orbitals so formed are directed towards the 4 corners of the tetrahedron. The angle between sp3 hybrid orbital is 109.5 as shown in figure 4.12. So this is the figure. Just you can have a look. Next, the structure of NH3 and H2O molecules can also be explained with the help of sp3 hybridization. In NH3, the valency shell outer electronic configuration of nitrogen in the ground state is 2s2, 2px1, 2py1, 2pz1, having 3 unpaired electrons in the sp3 hybrid orbitals, and a lone pair of electrons is present in the fourth one. These 3 hybrid orbitals overlap with 1s orbitals of hydrogen atom to form 3 NH sigma bonds. We know that the force of repulsion between a lone pair and a bond pair is more than the force of repulsion between 2 bond pairs of electrons. The molecule thus gets distorted and the bond angle is reduced to 107 degrees from 109.5 degrees. The geometry of such a molecule will be pyramidal as shown in figure 4.13. So this is 4.13. You can pause the video and you can check it. In case of H2O molecule, the 4 oxygen orbitals 1 2s and 3 2p undergo sp3 hybridization, forming 4 sp3 hybrid orbitals, out of which 2 contain 1 electron each and the other 2 contain a pair of electrons. These 4 sp3 hybrid orbitals acquire a tetrahedral geometry with 2 corners occupied by hydrogen atoms while the other 2 by the lone pairs. The bond angle in this case is reduced to 104.5 degrees from 109.5 degrees, and the molecule thus acquires a V shape or angular geometry. So this is the figure. You can just have a look at it. Next, other examples of sp3, sp2 and sp hybridization. sp3 hybridization in C2H6 molecule. In ethane molecule, both the carbon atoms assume sp3 hybrid state. One of the 4 sp3 hybrid orbitals of carbon atom overlaps axially with similar orbitals of other atom to form sp3 to sp3 sigma bond, while the other 3 hybrid orbitals of each carbon atom are used in forming sp3 s sigma bonds with hydrogen atoms as discussed in section 4.6.1. Therefore, in ethane, C single bond C bond length is 154 pm and each CH bond length is 109 pm. Next, sp2 hybridization in C2H4. In the formation of ethene molecule, one of the sp2 hybrid orbitals of carbon atom overlaps axially with sp2 hybridized orbital of another carbon atom to form CC sigma bond, while the other 2 sp2 hybrid orbitals of each carbon atom are used for making sp2 s sigma bond with two hydrogen atoms. The unhybridized orbitals 2px or 2py of one carbon atom overlaps sidewise with a similar orbital of the other carbon atom to form weak pi bond, which consists of two equal electron clouds distributed above and below the plane of carbon and hydrogen atoms. Thus, in ethene molecule, the carbon-to-carbon bond consists of one sp2 to sp2 sigma bond and one pi bond between p orbitals, which are not used in the hybridization and are perpendicular to the plane of molecule. The bond length 134 pm. The CH bond is sp2 s sigma with bond length 108 pm. The HCH bond angle is 117.6 degrees, while the HCC angle is 121 degrees. The formation of sigma and pi bonds in ethane is shown in figure 4.15. So this is the figure 4.15. You can pause it and go through it. Next is sp hybridization in C2H2. In the formation of ethyl molecule, both the carbon atoms undergo sp hybridization having two unhybridized orbital, that is 2py and 2px. One sp hybrid orbital of one carbon atom overlaps axially with sp hybrid orbital of the other carbon atom to form cc sigma bond, while the other hybridized orbital of each carbon atom overlaps axially with the half-filled s orbital of hydrogen atoms, forming sigma bond. Each of the two unhybridized p orbitals of both the carbon atoms overlaps sidewise to form two pi bonds between the carbon atoms. So, the triple bond between the two carbon atoms is made up of one sigma and two pi bonds as shown in figure 4.16. So, where is 4.16? Okay, this is 4.16. You can check it out. Okay, these figures. Next is hybridization of elements involving d orbitals. The elements present in the third period contain d orbitals in addition to s and p orbitals. The energy of the 3d orbitals are comparable to the energy of the 3s and 3p orbitals. The energy of the 3d orbitals are also comparable to those of 4s and 4p orbitals. As a consequence, the hybridization involving either 3s, 3p and 3d or 3d, 4s and 4p is possible. However, since the difference in energies of 3p and 4s orbitals is significant, no hybridization involving 3p, 3d and 4s orbitals is possible. The important hybridization schemes involving s, p and d orbitals are summarized below. So this is the table. Next, formation of PCl5 sp3d hybridization. The ground state and the excited state outer electronic configuration of phosphorus are represented below. Okay, this is the sp3d hybrid orbitals filled by electron pairs donated by 5 chlorine atoms. Now the 5 orbitals, that is 1s, 3p and 1d orbital, are available for hybridization to yield a set of 5 sp3 hybrid orbitals which are directed towards the 5 corners of a trigonal bipyramidal as depicted in figure 4.17. So this is the figure. Okay. It should be noted that all the bond angles in trigonal bipyramidal geometry are not equivalent. In PCl5, the 5 sp3d orbitals of phosphorus overlap with the singly occupied p orbitals of chlorine atoms to form 5 PCl sigma bonds. 3 PCl bonds lie in one plane and make an angle of 120 degrees with each other. These bonds are termed as equatorial bonds. The remaining 2 PCl bonds, one lying above and the other lying below the equatorial plane, make an angle of 90 degrees with the plane. These bonds are called axial bonds. As the axial bond pairs suffer more repulsive interaction from the equatorial bond pairs, therefore axial bonds have been found to be slightly longer and hence slightly weaker than the equatorial bonds, which makes PCl5 molecule more reactive. Next is formation of SF6, sp3d2 hybridization. In SF6, the central sulfur atom has a ground state outer electronic configuration 3s2 3p4. In the excited state, the available 6 orbitals, that is 1s, 3p and 2d, are singly occupied by electrons. These orbitals hybridize to form 6 new sp3d2 hybrid orbitals, which are projected towards the 6 corners of a regular octahedron in SF6. These 6 sp3d2 hybrid orbitals overlap with singly occupied orbitals of fluorine atoms to form 6 SF sigma bonds. Thus, SF6 molecule has a regular octahedral geometry as shown in figure 4.18. Where is 4.18? Okay, this is the figure. Octahedral geometry of SF6 molecule. Okay, you can check it out. Next is molecular orbital theory. Molecular orbital theory was developed by F. Hund and R. S. Mulliken in 1932. The salient features of this theory are: first one, the electrons in a molecule are present in the various molecular orbitals as the electrons of atoms are present in the various atomic orbitals. Second point, the atomic orbitals of comparable energies and proper symmetry combine to form molecular orbitals. Third point, while an electron in an atomic orbital is influenced by one nucleus in a molecular orbital, it is influenced by two or more nuclei depending upon the number of atoms in the molecule. Thus, an atomic orbital is monocentric while a molecular orbital is polycentric. Next point, the number of molecular orbital formed is equal to the number of combining atomic orbitals. When two atomic orbitals combine, the two molecular orbitals are formed. One is known as bonding molecular orbital, while the other is called anti-bonding molecular orbital. Next point, the bonding molecular orbital has lower energy and hence greater stability than the corresponding anti-bonding molecular orbital. Next point, just as the electron probability distribution around a nucleus in an atom is given by an atomic orbital, the electron probability distribution around a group of nuclei in a molecule is given by a molecular orbital. The molecular orbitals, like atomic orbitals, are filled in accordance with the Aufbau principle, obeying the Pauli's exclusion principle and the Hund's rule. Next is formation of molecular orbitals, linear combination of atomic orbitals, LCAO. According to wave mechanics, the atomic orbitals can be expressed by wave functions, which represent the amplitude of the electron waves. These are obtained from the solution of Schrödinger wave equation. However, since it cannot be solved for any system containing more than one electron, molecular orbitals, which are one electron wave functions for molecules, are difficult to obtain directly from the solution of Schrödinger wave equation. To overcome this problem, an approximate method known as linear combination of atomic orbitals, LCAO, has been adopted. Let us apply this method to the homonuclear diatomic hydrogen molecule. Consider the hydrogen molecule consisting of two atoms A and B. Each hydrogen atom in the ground state has one electron in 1s orbital. The atomic orbitals of these atoms may be represented by the wave functions psi A and psi B. Mathematically, the formation of molecular orbitals may be described by the linear combination of atomic orbitals that can take place by addition and by subtraction of wave functions of individual atomic orbitals as shown below. Psi MO equals to psi A plus or minus psi B. Therefore, the two molecular orbitals sigma and sigma star are formed as sigma equals to psi A plus psi B, sigma star equals to psi A minus psi B. The molecular orbital psi formed by the addition of atomic orbitals is called the bonding molecular orbital, while the molecular orbital psi star formed by the subtraction of atomic orbital is called anti-bonding molecular orbital, as depicted in figure 4.19. So here is 4.19. Okay, you can see this, right? Qualitatively, the formation of molecular orbitals can be understood in terms of the constructive or destructive interference of the electron waves of the combining atoms. In the formation of bonding molecular orbital, the two electron waves of the bonding atoms reinforce each other due to constructive interference, while in the formation of anti-bonding molecular orbital, the electron waves cancel each other due to destructive interference. As a result, the electron density in a bonding molecule orbital is located between the nuclei of the bonded atoms, because of which the repulsion between the nuclei is very less, while in case of an anti-bonding molecular orbital, most of the electron density is located away from the space between the nuclei. In fact, there is a nodal plane on which the electron density is zero between the nuclei, and hence the repulsion between the nuclei is high. Electrons placed in a bonding molecular orbital tend to hold the nuclei together and stabilize a molecule. Therefore, a bonding molecular orbital always possesses lower energy than either of the atomic orbitals that have combined to form it. In contrast, the electrons placed in the antibonding molecular orbital destabilize the molecule. This is because the mutual repulsion of the electrons in this orbital is more than the attraction between the electrons and the nuclei, which causes a net increase in energy. It may be noted that the energy of the anti-bonding orbital is raised above the energy of the parent atomic orbitals that have combined, and the energy of the bonding orbital has been lowered than the parent orbitals. The total energy of the two molecular orbitals, however, remains the same as that of the two original atomic orbitals. Next is conditions for the combination of atomic orbitals. The linear combination of atomic orbitals to form molecular orbitals takes place only if the following conditions are satisfied. First one, the combining atomic orbitals must have the same or nearly the same energy. This means that 1s orbital can combine with another 1s orbital but not with 2s orbital, because the energy of 2s orbital is appreciably higher than that of 1s orbital. This is not true if the atoms are very different. Second point, the combining atomic orbitals must have the same symmetry about the molecular axis. By convention, z-axis is taken as the molecular axis. It is important to note that atomic orbitals having same or nearly the same energy will not combine if they do not have the same symmetry. For example, 2pz orbital of one atom can combine with 2pz orbital of the other atom, but not with the 2px or 2py orbitals because of their different symmetries. Next point, the combining atomic orbitals must overlap to the maximum extent. Greater the extent of overlap, the greater will be the electron density between the nuclei of the molecular orbital. Next one, types of molecular orbitals. Molecular orbitals of diatomic molecules are designated as sigma, pi, delta, etc. In this nomenclature, the sigma molecular orbitals are symmetrical around the bond axis, while pi molecular orbitals are not symmetrical. For example, the linear combination of 1s orbitals centered on two nuclei produces two molecular orbitals which are symmetrical around the bond axis. Such molecular orbitals are of the sigma type and are designated as sigma 1s and sigma star 1s. If internuclear axis is taken to be in the z direction, it can be seen that a linear combination of two pz orbitals of two atoms also produces two sigma molecular orbitals designated as sigma 2pz and sigma star 2pz. Molecular orbitals obtained from 2px and 2py orbitals are not symmetrical around the bond axis because of the presence of positive lobes above and negative lobes below the molecular plane. Such molecular orbitals are labeled as pi and pi star. A pi bonding MO has larger electron density above and below the internuclear axis. The pi star anti-bonding MO has a node between the nuclei. Next is energy level diagram for molecular orbitals. We have seen that 1s atomic orbitals on two atoms form two molecular orbitals designated as sigma 1s and sigma star 1s. In the same manner, the 2s and 2p atomic orbitals, 8 atomic orbitals on two atoms gives rise to following 8 molecular orbitals. Antibonding and bonding. Okay, you can check it out. You can pause and check it. Next is figure 4.20 also. Just okay, I'll focus it. You can pause and check it. Okay. The energy levels of these molecular orbitals have been determined experimentally from spectroscopic data for homonuclear diatomic molecules of second row elements of the periodic table. The increasing order of the energies of various molecular orbitals for O2 and F2 is given below. This is the one. You can please look at it. However, this sequence of energy levels of molecular orbitals is not correct for the remaining molecules Li2, Be2, B2, C2, N2. For instance, it has been observed experimentally that for molecules such as B2, C2, N2, etc., the increasing order of energies of various molecular orbitals is this one. The important characteristic feature of this order is that the energy of sigma 2pz molecular orbital is higher than that of pi 2px and pi 2py molecular orbitals. Next is electronic configuration and molecular behavior. The distribution of electrons among various molecular orbitals is called electronic configuration of the molecule. From the electronic configuration of the molecule, it is possible to get important information about the molecule as discussed below. Next is stability of molecules. If Nb is the number of electrons occupying bonding orbitals and Na the number occupying the antibonding orbitals, then first point, the molecule is stable if Nb is greater than Na, and second point, the molecule is unstable if Nb is less than Na. In first one, more bonding orbitals are occupied and so the bonding influence is stronger and a stable molecule results. In second one, the anti-bonding influence is stronger and therefore the molecule is unstable. Next, bond order. Bond order is defined as one half the difference between the number of electrons present in the bonding and the anti-bonding orbitals. Bond order equals to 1 by 2 Nb minus Na. The rules discussed above regarding the stability of the molecule can be restarted in terms of bond order as follows. A positive bond order means a stable molecule, while a negative or zero bond order means an unstable molecule. Next, nature of the bond. Integral bond order values of 1, 2 or 3 correspond to single, double or triple bonds respectively as studied in the classical concept. Bond length. The bond order between two atoms in a molecule may be taken as an approximate measure of the bond length. The bond length decreases as bond order increases. Next, magnetic nature. If all the molecular orbitals in a molecule are doubly occupied, the substance is diamagnetic, repelled by magnetic field. However, if one or more molecular orbitals are singly occupied, it is paramagnetic, attracted by magnetic field. Example, O2 molecule. Next is bonding in some homonuclear diatomic molecules. In this section, we shall discuss bonding in some homonuclear diatomic models. First one, diatomic molecules. Okay, first one, hydrogen molecule H2. It is formed by the combination of two hydrogen atoms. Each hydrogen atom has one electron in one s orbital. Therefore, in all there are two electrons in hydrogen molecules which are present in sigma 1s molecular orbital. So, electronic configuration of hydrogen molecule is sigma 1s2. The bond order of H2 molecule can be calculated by as given below. Bond order equals to Nb minus Na by 2 equals to 1. This means that the two hydrogen atoms are bonded together by single covalent bond. The bond dissociation energy of hydrogen molecule has been found to be 438 kilojoules per mole and bond length equal to 74 pm. Since no unpaired electron is present in hydrogen molecule, therefore it is diamagnetic. Next is helium molecule. The electronic configuration of helium atom is 1s2. Each helium atom contains 2 electrons. Therefore, in He2 molecule, there would be 4 electrons. These electrons will be accommodated in sigma 1s and sigma star 1s molecular orbitals, leading to electronic configuration sigma 1s2, sigma star 1s2. Bond order of He2 is 0. He2 molecule is therefore unstable and does not exist. Similarly, it can be shown that Be2 molecule also does not exist. Next is lithium molecule. The electronic configuration of lithium is 1s2 2s1. There are 6 electrons in Li2. The electronic configuration of Li2 molecule therefore is Li2 sigma 1s2, sigma star 1s2, sigma 2s2. The above configuration is also written as sigma 2s2, where Kk represents the closed K shell structure, sigma 1s2, sigma star 1s2. From the electronic configuration of Li2 molecule, it is clear that there are 4 electrons present in bonding molecular orbitals and 2 electrons present in anti-bonding molecular orbitals. Its bond order therefore is 1 by 2, 4 minus 2 equals to 1. It means that Li2 molecule is stable, and since it has no unpaired electrons, it should be diamagnetic. Indeed, diamagnetic Li2 molecules are known to exist in the vapor phase. Next is carbon molecule C2. The electronic configuration of carbon is 1s2, 2s2, 2p2. There are 12 electrons in C2. The electronic configuration of C2 molecule therefore is sigma 1s2, sigma star 1s2, sigma star 2s2, pi 2px2 equals to pi 2py2. The bond order of C2 is 2. And C2 should be diamagnetic. Diamagnetic C2 molecules have indeed been detected in vapor phase. It is important to note that double bond in C2 consists of both pi bonds because of the presence of 4 electrons in 2 pi molecular orbitals. In most of the other molecules, a double bond is made up of sigma bond and a pi bond. In a similar fashion, the bonding in N2 molecule can be discussed. Next is oxygen molecule O2. The electronic configuration of oxygen atom is 1s2, 2s2, 2p4. Each oxygen atom has 8 electrons. Hence, in O2 molecule there are 16 electrons. The electronic configuration of O2 molecule therefore is this one. You can check it out. From the electronic configuration of O2 molecule, it is clear that 10 electrons are present in bonding molecular orbitals and 6 electrons are present in the anti-bonding molecular orbitals. Its bond order therefore is 2. So, in oxygen molecule, atoms are held by a double bond. Moreover, it may be noted that it contains 2 unpaired electrons in psi star 2px and psi star 2py molecular orbitals. Therefore, O2 molecule should be paramagnetic, a prediction that corresponds to experimental observation. In this way, the theory successfully explains the paramagnetic nature of oxygen. Similarly, the electronic configuration of other homonuclear diatomic molecules on the second row of the periodic table can be written. In figure 4.21 are given the molecular orbital occupancy and molecular properties for B2 through Ne2. The sequence of MOs and their electron population are shown. The bond energy, bond length, bond order, magnetic properties and valency electron configuration appear below the orbital diagrams. Okay, so this is the figure 4.21. You can check it out. Okay, you can pause it and please check it. Next, hydrogen bonding. Nitrogen, oxygen and fluorine are the highly electronegative elements. When they are attached to the hydrogen atom to form covalent bond, the electrons of the covalent bond are shifted towards the more electronegative atom. This partially positively charged hydrogen atom forms a bond with the other more electronegative atom. This bond is known as hydrogen bond and is weaker than the covalent bond. For example, in HF molecule, the hydrogen bond exists between hydrogen atom of one molecule and fluorine atom of another molecule as depicted below. This is the one. Here, hydrogen bond acts as a bridge between two atoms which holds one atom by covalent bond and the other by hydrogen bond. Hydrogen bond is represented by a dotted line, while a solid line represents the covalent bond. Thus, hydrogen bond can be defined as an attractive force which binds hydrogen atom of one molecule with the electronegative atom of another molecule. Next, cause of formation of hydrogen bond. When hydrogen is bonded to strongly electronegative element X, the electron pair shared between the two atoms move far away from hydrogen atom. As a result, the hydrogen atom becomes highly electropositive with respect to the other atom X. Since there is displacement of electrons towards X, the hydrogen acquires fractional positive charge, while X attains fractional negative charge. This results in the formation of a polar molecule having electrostatic force of attraction, which can be represented as this. You can check it. The magnitude of H bonding depends on the physical state of the compound. It is maximum in the solid state and minimum in the gaseous state. Thus, the hydrogen bonds have strong influence on the structure and properties of the compounds. Next, types of H bonds. There are two types of H bonds. First one, intermolecular hydrogen bond. Second one, intramolecular hydrogen bond. First one, intermolecular hydrogen bond. It is formed between two different molecules of the same or different compounds. For example, H bond in case of HF molecule, alcohol or water molecules, etc. Next one, intramolecular hydrogen bond. It is formed when hydrogen atom is in between the two highly electronegative atoms present within the same molecule. For example, in O-nitrophenol, the hydrogen is in between the two oxygen atoms. You can check the figure over here. Next is a summary of the lesson. Cosel's first insight into the mechanism of formation of electropositive and electronegative ions related the process to the attainment of noble gas configurations by the respective ions. Electrostatic attraction between ions is a cause for their stability. This gives the concept of electrovalency. The first description of covalent bonding was provided by Lewis in terms of the sharing of electron pair between atoms, and he related the process to the attainment of noble gas configurations by reacting atoms as a result of sharing of electrons. The Lewis dot symbols show the number of valency electrons of the atoms of a given element, and Lewis dot structures show pictorial representations of bonding in molecules. An ionic compound is pictured as a three-dimensional aggregation of positive and negative ions in an ordered arrangement called the crystal lattice. In a crystalline solid, there is a charge balance between the positive and negative ions. The crystal lattice is stabilized by the enthalpy of lattice formation. While a single covalent bond is formed by sharing of an electron pair between two atoms, multiple bonds result from the sharing of two or three electron pairs. Some bonded atoms have additional pairs of electrons not involved in bonding. These are called lone pairs of electrons. A Lewis dot structure shows the arrangement of bonded pairs and lone pairs around each atom in a molecule. Important parameters associated with chemical bonds like bond length, bond angle, bond enthalpy, bond order, and bond polarity have significant effect on the properties of compounds. A number of molecules and polyatomic ions cannot be described accurately by a single Lewis structure, and a number of descriptions based on the same skeletal structure are written, and these taken together represent the molecule or ion. This is a very important and extremely useful concept called resonance. The contributing structures or canonical forms taken together constitute the resonance hybrid, which represents the molecule or ion. The VSEPR model used for predicting the geometrical shapes of molecules is based on the assumption that electron pairs repel each other and therefore tend to remain as far apart as possible. According to this model, molecular geometry is determined by repulsions between lone pairs and lone pairs, lone pairs and bonding pairs, and bonding pairs and bonding pairs. The order of these repulsions being given over here, you can check it. The valency bond VB approach to covalent bonding is basically concerned with the energetics of covalent bond formation, about which the Lewis and VSEPR models are silent. Basically, the VB theory discusses bond formation in terms of overlap orbitals. For example, the formation of the H2 molecule from two hydrogen atoms involves the overlap of the 1s orbitals of the two H atoms which are singly occupied. It is seen that the potential energy of the system gets lowered as the two H atoms come near to each other. At the equilibrium internuclear distance, bond distance, the energy touches a minimum. Any attempt to bring the nuclei still closer results in a sudden increase in energy and consequent destabilization of the molecule. Because of orbital overlap, the electron density between the nuclei increases, which helps in bringing them closer. It is, however, seen that the actual bond enthalpy and bond length values are not obtained by overlap alone, and the other variables have to be taken into account. For explaining the characteristic shapes of polyatomic molecules of Pauling introduced the concept of hybridization of atomic orbitals. sp, sp2, sp3 hybridization of atomic orbitals of beryllium, boron, carbon, nitrogen and oxygen are used to explain the formation and geometrical shapes of molecules like BeCl2, BCl3, CH4, NH3 and H2O. They also explain the formation of multiple bonds in the molecules like C2H2 and C2H4. The molecular orbital theory describes bonding in terms of the combination and arrangement of atomic orbitals to form molecular orbitals that are associated with the molecule as a whole. The number of molecular orbitals are always equal to the number of atomic orbitals from which they are formed. Bonding molecular orbitals increase electron density between the nuclei and are lower in energy than the individual atomic orbitals. Antibonding molecular orbitals have a region of zero electron density between the nuclei and have some energy than the individual atomic orbitals. The electronic configuration of the molecules is written by filling electrons in the molecular orbitals in the order of increasing energy levels. As in the case of atoms, the Pauli exclusion principle and Hund's rule are applicable for the filling of molecular orbitals. Molecules are said to be stable if the number of electrons in bonding molecular orbitals is greater than that in an antibonding molecular orbitals. Hydrogen bond is formed when a hydrogen atom finds itself between two highly electronegative atoms such as F, O and N. It may be intermolecular, existing between two or more molecules of the same or different substances, or intramolecular, present within the same molecule. Hydrogen bonds have a powerful effect on the structure and properties of many compounds. So with this we are done with the lesson. If you have any doubts, you can post it in the comment box. If you like it, please share to your friends. You also like and subscribe the channel. And the figures and the problems and solutions, everything will be given at the end of this audiobook. You can check it out. Okay, thank you.